Right, so things are looking pretty good for LTP, right? We've got this clear-cut evidence that learning and memory appears to be dependent on the NMDA receptor, and that LTP looks to be dependent on the NMDA receptor, and it matches all of these theoretical ideas for what a cellular mechanism of learning and memory should look like, except for one little thing that we've kind of a little bit skipped over. Okay, so what did Hebb say again? He said when an axon of cell A is near enough to excite cell B and repeatedly or persistently takes part in firing it, some growth process happens that makes the synapse stronger, right? So it's taking part in firing it. It's causally related to firing it. We need cell A to make cell B fire. How how could a cell establish that, right? How could a cell know whether or not a synapse was actually important for making a cell fire an action potential? Well, temporal information contains a lot of information about causation, right? So if event A happens after event B, then event A cannot have caused event B, right? So, if I slip on some ice and then I drink 2 pints of beer, I cannot have slipped on the ice because I drank the beer. It seems pretty straightforward. It doesn't, of course, mean that if I drink some beer and then slip on the ice, I slipped on the ice because I drank some beer. It's just that if the pairing is the other way around, it rules out the causal relationship, i.e., if A happens after B, then A cannot have caused B. So, from that logic, I'm going to assert that if the EPSP arrives after the spike, then the EPSP cannot have taken part in firing the cell. Enter Henry Markram working with Sackman. So he's got a paired recording. He's got a recording from cell A, a recording from cell B, and when he makes cell A fire, he sees an EPSP in cell B. So what he's going to do is he's going to excite cell A, see the EPSP, and inject current into cell B to make the cell fire, because just the connection from one neuron to another neuron is usually not strong enough to do that. But he's going to vary the time with where he stimulates the postsynaptic cell to fire the action potential. He'll either do it before the EPSP, where here this EPSP cannot have caused the spike because it was at the wrong time, or here, right, where there is the EPSP first and then the spike, where this EPSP could have caused the spike. And what he shows is that when you have the causal order, you get some LTP, and when you have the anti-causal order, you get some LTD. So if this postsynaptic spike happens before the EPSP, then those EPSPs, the synapses that mediate those EPSPs, get smaller. But if the EPSP lands and then the cell spikes, then the synapses that mediated that EPSP can get stronger. Now, Mooming Poo did the same experiment, but showed it in a much nicer way, right? So here we see the timing between the presynaptic input and the postsynaptic firing, or if you're just firing and firing. And what she showed was that so long as there is a little difference so that the presynaptic cell fires just a bit before the postsynaptic cell, and really it's like 5 milliseconds, then you can get very strong LTP. But as they move out in time, and basically much more than 40 milliseconds, then you get nothing. While if the relationship is anti-causal, so the postsynaptic cell fires an action potential and then the EPSP comes in, then the EPSPs get weaker. Though again, it's basically once you get beyond 40 milliseconds, there's no effect. So there's a sort of 40 millisecond window where the timing of the EPSP and the action potential seem to really matter. Now, what is the cellular mechanism of this? Well, it's kind of the same as what we learned before. We've got these NMDA receptors. To open them up, you need to depolarize the cell. Well, when you perform on this side, on the spike timing dependent plasticity graph, what's happening is when the postsynaptic cell fires an action potential, you get a back propagating action potential that lands at the synapse in time to cause the NMDA receptors to open. While if you do it in the other direction, the backpropagating action potential doesn't land at the same time as the EPSP, and so you get no effect. Now, exactly then why you get a little LTP, a little LTD is unclear. But the point is, it's the backpropagating action potential plus the EPSP timed so they line up just right for the NMDA receptor to open leads to LTP.